Welcome to Miami and welcome to IMSA. IMSA is an institute supported by University of Miami and the Simons Foundation. So today we all get together to celebrate the contributions of Lefschetz to mathematics, but to cooperation between Americas as well. So for many of us, Lefschetz is a personal hero. Of course, he's a legend, and he produced many living legends like Dennis, John, Philip, Carlos, there are with us today. But as I mentioned, he also paid a lot of attention to the cooperation with Latin America, and more is going to be said about this today. So let me give the opportunity to the University of Miami provost, Willie Brado, to open the conference.
Good morning, everybody. Good morning. Try one more time. Good morning, everyone. Good morning. So I know, trust me, I understand. So thank you all for inviting me to be here. I love it. It really is a pleasure. I just came from literally across that auditorium where I was standing in front of a room of incredibly talented people doing work in resilience. And now I have the pleasure and honor to be in an equally talented room with all of you to sort of honor someone who has been a member of the National Academy of Science. We're celebrating our 100th anniversary. So any members from the National Academy of Science? Oh, right in front of me. All right, so for the sister agency, I'm a member of the National Academy of Medicine. So they do a lot of collaboration with National Academy of Science. So thank you all so much for being here. A real special thank you to Ludlow. The Institute for Mathematical Sciences of the Americas is one of the gems here at the University of Miami. It constantly puts on programming such as the one that we are here today. And we look forward to all of the great things that IMSA has continued to do over the years with the support for private donors and the Science Foundation. We hope that eventually from the National Science Foundation as well. And to all of you, so thank you so much for being here. It is really a great time to be here at the University of Miami. We will be celebrating our 100th birthday as well on April 8th. So we hope that everybody who is not from Miami is able to come back and to partake in some of our activities that we'll have throughout the week. So with that said, I'm going to turn it over back to you, Ludlow, and thank you all so much for being here.
Thank you, Rich. So let's start with our work. And it's an immense pleasure to introduce Mr. Norman Hodge-theoretic, great scientist, humanitarian, and friend of mine for 37 years. Carlos, okay. Carlos is going to tell us about Lefschetz, devissage, and Hodge-theoretic.
Okay, thank you very much. Thank you very much, Lino. It's a great pleasure to be here in Miami. A great pleasure to be able to participate in this conference to honor Lefschetz, who was, as Lino said, he was one of the first people, I think, to look at algebraic geometry and topology. So I'd like to try to trace a little bit. This is going to be a sort of historical talk, so I'd like to try to trace the flow of ideas that started from Lefschetz's work on what we now know as Lefschetz pencils and those sorts of things, and leading up to Hodge theory and modern viewpoints on Hodge theory. Okay, so let me start. Okay, so suppose we have X, which is suppose we have X, which is a smooth projective variety inside some projective space. So we'll work over the complex numbers here, but as you'll see on a couple of the screenshots, I mean, most of what's said here also works in positive characteristic, or some of what's said works in positive characteristic in some way. That's an important part of the history also. Okay, so now what do we do? So choose A, which is a P n minus 2 contained inside the Pn. General. Okay, and let's let delta be a intersect text. Okay, this is going to be the center. Okay, so and then we have P1 is a set of hyperplanes containing A, which is contained in the dual Pn. Okay. This again is a general. This is a general line inside the dual P. Yeah. Okay. And now let's let y mapping text either blow up along delta, and then we get a map from y into P1. This is called the Lefschetz pencil. Wait, let me tell you. How do I turn the page? You'll just go like that.
Yeah, just go up there.
Ah, okay. Okay, so maybe so now I should have said here. So we're going to be looking at this. And so what was Lefschetz's work really? I mean, not all, but some initial point. The idea is to use the function f to study the topological space, X topological. This is in the book Analysis situs. Okay. So this is in French. Lefschetz grew up in Paris, as I understand. He wasn't born in Paris, but he grew up in Paris. So this was written in French. So this is not. I mean, you couldn't say this is the origins of topology, and I think you couldn't really necessarily say it's the origins of looking at complex geometry as topology, because there were other people before that, Poincaré, Picard. An interesting point I noted is that Lefschetz was following in Paris, was following the math course of M. Picard, for example, among others. But this it really represents the starting point of the study of the construction, which you start with an algebraic variety and you get a topological space. And this is something that we're still studying today. Okay, so and not only is it something we're still studying today, but in fact the viewpoint that Lefschetz used, for one thing, it's still the main way of using studying the question. And for another thing, as I'd like to show, really led to a lot of the development of the techniques that we use today. Okay, so now I'd like to go. I did a few screenshots very quickly when I noticed that we weren't talking about the board here. This is an interesting point. So this is a useful paper because Pamutka wrote a paper where he explained in modern language the arguments that Lefschetz was using, some of the arguments that Lefschetz was using.
Sorry, this is not in the right order. Okay, so I wanted to say I found also an interesting thing, which is a review by Alexander. So this is the start of the review. That's the signature of the review on the next page. And there's a very interesting phrase in this review, which is here, starting from it would be. So Alexander says, it would be interesting, so he's reviewing Lefschetz's paper, Lefschetz's book. He said, it would be interesting to see how far the theory of algebraic manifolds could be carried without making use of anything more than the group of linear transformations engendered on the cycles gamma I. Those are the vanishing cycles. So this is, I think this is a nice phrase because this sort of opened up. I mean, maybe not directly from the phrase, but this idea was really put into play by many people, including many people who are here, such as Mina Hiker with Moishe Zahn, Lou Mill, Aru Donaldson, Yoto, and others on the study of phrase monodromy, for example. And it's also going to be a little bit the leitmotif of what I like to say today. I'm not sure what Alexander meant exactly when he said that, but I think we can sort of take it as an indication. Okay, so now let me just make a couple of comments. So the point is that we have y mapping to x. So we have delta cross P1 is contained inside y. That's the exceptional locus, okay. And then we can look at R in modern language. We can look at R I F lower star of Q Y. Now, so this is the local system of monodromy representations. This is the monodromy local system for Lefschetz pencil. And so one of the main facts in Lefschetz theory is that it's constant. So let's say n is the dimension of x. So the fibers of the Lefschetz pencil are hyperplane sections of x with their dimension n-1. So their middle dimension of the cohomology is n-1. Oh, sorry. Now I have to figure out how to erase things here. Okay. So in degrees different from the middle dimension, the monodromy local system is constant. And for I equals n, it has a constant part. And the variable. Okay. All right. I equals n. Sorry. The constant part and the variable part. The constant part corresponds to, in the Lefschetz hyperplane theorems, corresponds to the cohomology of x in degree n-1, basically. But now something that we know is that a theorem is that the variable part is a simple representation, is an irreducible representation. Irreducible as a representation, let's say. what? Is irreducible as a representation of pi one as the complement of the singular pi. Okay. So now let me just say what's going on here. So we have P1 maps into P and dual, and inside P and dual we have the dual variety. Okay, and then so if we take P1 intersect the dual variety, this is going to be a finite set of points. P1 to TK. Okay. And so one of the first main theorems, so the starting point, is that the hyperplanes, the hyperplane sections that's for Healy's theorem are smooth if he is different from one of these singular points. But so the main point is that the HTI have simple double plots. Okay. And this is in fact, HTI is tangent to X at a point PI, and Hessian is non-degenerate. Okay. So the Hessian is the Hessian gives you a quadratic form on the tangents, on the projective tangent space, you know, the hyperplane side, and that defines a quadratic cone inside the tangent space, which is oh yeah, where did I know she left. Now we're in trouble. Something seems to have stopped here. Where's the plug? Is that Rodolfo? Okay. Does anybody know how to make this bigger, or we have to open a new? Yeah, I guess we're so. Okay, well, sorry, I guess we don't have the previous slide, but sorry about this. But if anything, this is maybe motivation to prepare your slides. I'm sorry about this. Okay, so we just have a little lemma, which is that this is an interesting little exercise, in fact. So exercise. Then the Hessian matrix is non-degenerate at a general point. By the Hessian, I mean the Hessian matrix of the expression of X as a function, you know, as the graph of a function. Locally at that point. Okay. So we can just see what's the sort of the idea of the proof is that if after projection and so on, if X equals the graph of G from, let's say, C n to Cn plus 1, then the Gauss map, so then the basically given by the partial derivatives. And having the image of the Gauss map be so in this case, by projection, we can reduce to the case where you just have a graph of a function. I'm sorry. Inside Cn plus 1, the graph of a function, just a single value function. Then the Gauss map is basically given by this vector, the gradient. And the fact that if the Gauss map is the image has dimension n, if and only if at a general point, the Jacobian of this thing is non-degenerate. But the Jacobian of that guy is Hessian. What I'm calling Hessian.
Okay, so having a Gauss map whose image has the correct dimension tells you that the hyperplane the tangent hyperplanes are going to touch, going to cut X in a simple level point. Okay. And if the dual variety has a smaller dimensions, that actually exists. If the dual variety has a smaller dimension, then a general P1 will actually not intersect the variety. So you don't care. There's no singular points in that case. Okay, so then that leads you to the theory. So that we have the theory of the Lefschetz transformation. And so if n, okay, so n was the dimension of x, n minus 1 odd, then there's symplectic transections. And if n is even, then they're reflections. Okay. And so if n is odd, the action on cohomology looks like this. If n is even, then the action on cohomology just has a single -1 eigenvalue. So the monodromy representation of the local system has generators when you go around each of the singular points, which are matrices of this form. One of these more. Always the same.
Okay. Now, furthermore, so either the reflection or the transection corresponds to a vanishing cycle. At that point, okay. And these are all conjugate. These are all conjugate under the monodromy representation. The reason for that is that the dual variety is irreducible. So in particular, the open set of general points is connected. And this gives the proof of the irreducibility. So let me go back to my screenshots here. So this is a little bit also bibliography. So one good reference is Deligne's paper, Projective 1, where he has sections on Lefschetz theory. And here he gives a table about the monodromy transformations. So this is the form of either the transection or the reflection. Okay, so now we get to the point which is maybe the first thing you would think of after Lefschetz's paper. It's not completely clear whether, I didn't look at the original book, I'm sorry. But from the discussion, it's not completely clear whether Lefschetz really went exactly to this distance. But in any case, we would like to we'd like to look at the Leray spectral sequence. For the map from Y to Q1, okay. And so this is going to have three parts. So we're going to have one thing, it degenerates. This is a general thing proven by Deligne in his book about Lefschetz theory. And there's three parts, degenerates at E2. There's three parts. There's H0 of R I F lower star Q. H1 of R I minus 1 F lower star Q. And H2 of R I minus 2 F lower star Q. Now for I equals n, then this part of course, these all contribute to H n of Y, but in fact, it contributes to the new, to the middle cohomology, the primitive. Now let me just put up another screenshot. So another reference here. Another reference did I? Wait, this is in SGA7. Like gas. Okay. So SGA7 is a whole book about Lefschetz theory. So you can see how this developed, obviously. And so this is a subtle point which I actually have to say I hadn't really thought of before starting to look at the talk. Which is that if we look at the H1, the term, the E1 term of the E2 one term of the spectral sequence, which is H1 of Q1, Rn minus 1 lower star of QL. That gives you the primitive cohomology of X, plus another piece, which is the vanishing part of the cohomology of the center of the blow-up. Okay. So let's just sort of quickly look at this. Right, so remember that we had delta as the center of the blow-up. And so main first part in Lefschetz's book is that we have an exact sequence. So hi of x q maps to hi of y maps to hi minus 2 of delta. This is a split exact sequence. Okay. That's because the exceptional locus is delta across P1. So what does this mean? So the point here is that delta is a complete intersection of two hyperplane sections. So the h n minus 2 of delta has a new piece mapping to 0 in h. Well, the family elliptic curves on P2. So Lefschetz pencil, the family elliptic curves on P2. If you check the degree of the varieties embedding, it's n, what is that? It's 3 times 4 basically, so it's 12. That means that the Lefschetz pencil has 12 singular fibers. The cohomology of P1 minus 12 points with a rank 2 local system. So the cohomology of the elliptic curve fiber has rank 2. So a rank 2 local system. So our local system is a rank 2 local system. The cohomology on P1 minus 12 points of a rank 2 local system has dimension 20. It's 12 minus 2, which is 10, multiplied by the rank, which is 2. Okay. And then that's the cohomology of the open piece. Then you have to add in one term for each singular point because of the vanishing cycle. The cohomology of the sheaf over P1. You have to subtract those 12. So 20 minus 12 equals 8. And so this delta in that case is 9 points, right? It's the intersection of two cubics. And of course the degree 0 cohomology of X is just one dimensional. So instead of 9, you get 1. So the defect here, this vanishing part of the cohomology, that's 8-dimensional, which is 20 minus 12. So having done an example, you can believe the statement. Anyway, okay, so I think that's a somewhat interesting point. But I have to say, I'm not sure, but maybe look on those. This sounds a little bit like go into Gifford models and so on. But it seems to me a little mysterious how exactly this cohomology, the new cohomology of the codimension 2 complete intersection, how does it sort of find its way into the R1, into the H1 of R1 of R minus 1 F lower star of Q? That doesn't seem obvious to me. So I'm not sure, as I said, I don't know whether somebody's already looked at that or not, so I don't know whether that's a question we'll get or not, but possible. So now I'd like to start from here. Okay, so this is sort of the original part of what happened in Lefschetz theory. Okay, so now what about Hodge theory? Okay. We can see this, if you want to look at Lefschetz's influence, you can really see a beginning of Hodge theory because of the Lefschetz 1-1 theorem. Right, so the Lefschetz 1-1 theorem in the modern terminology says that if you look at the integral cohomology inside the Hodge decomposition of H2, then the integral cycle or line inside H1-1 have to be come from line level. It wasn't necessarily phrased in those terms in the 1920s. But so anyway, but that's clearly one of the inputs into Hodge theory. But so what does Hodge theory basically say? The basic thing is that the complex value cohomology of X has a Hodge decomposition. And this comes from but it's not the same delta, this is Laplacian. So the sort of the reason why we have this is that we have the Gauge identities that tell you that the D Laplacian and the del R Laplacian are the same. One, macro two. And so the kernel of the del R Laplacian decomposes according to the degree of performance. That's the way you can see the Hodge composition. Okay, so I'm not sure if, I mean, Phil will maybe be able to comment more about to what extent was Lefschetz's picture with Lefschetz pencils exactly one of the motivating examples, but I'm assuming it was at least among the motivating examples for this. So in our family of varieties F from Y mapping to P1, each fiber has a Hodge decomposition. So H, let's say we'll take n minus 1, Hn minus 1 of Y sub t Y sub t is the hyperplane for the value t. Okay, so well, let's call these VPQ. And these vary in what's called a variation of Hodge structure. So read it down. The exact means variation of Hodge. So this tells us important properties of how these bundles vary with respect to the flat connection. So we have a flat connection. Often known called the Gauss-Bonnian connection. Okay. And these bundles have a specific pattern of how they vary as we move around in point keeping inside. So there's a natural question. How to get back the cohomology of X, or let's say, or just the part, the H1 of P1. So, because see what Lefschetz's theory said was that you can, in cohomology, you can get back to the cohomology of the total space or the cohomology of the original X, modulo the total delta. By looking at the cohomology of P1, which coefficient in this what's now known as a reverse sheet, I mean, the coefficients in this sheet, which is the Rn minus 1 at lower star of the constant. Okay, so this is underlying a variation of Hodge structure. And we'd like to be able to integrate the variation of Hodge structure into a Hodge decomposition on the cohomology of P1.
that we'd like to integrate this variation Hodge structure on. It's almost a local system. It's a local system over an open subset of P1, and it has a nice extension to P1.
We have a good control on the monodromy around the points and everything. Now, so Phil, I don't know, was this like the first thing you were thinking of, or did it come later? Because it really, I mean, so I'm about to say is that it really, technically speaking, goes all the way to Steve Zucker's theorem. But you can, in some way, you can really see that a lot of the original work on variation of Hodge structure, it's kind of motivated by that as a goal. Okay, so in order to do this, so this is to do this is Steve Zucker's theorem. But it requires the input of the whole theory. In particular, the theory of degenerations. Of the period mapping. I wrote some names in my abstract. Let me just say dot here.
It's a little dangerous to try to give a complete list of references for each kind of thing. Okay. But you can't really do, at least you can't really do the analytic theory needed for Steve Zucker's theorem without having some control on the asymptotic behavior of the Hodge, of this variation of Hodge structure as you're going towards the singular. That's what the whole degeneration of period mappings subject is all about.
Okay, so
now let me just sort of briefly say how this works. So because
I think this is also has a historical interest. So the technicalities of this.
So Steve Zucker actually refers to a letter from Deligne.
So that I suppose to start with, we have a smooth, a proper base S and a VHS over S.
Then what can we do? Then we can so we have
We have a C infinity isomorphism. Like that. And the flat connection let me write it this way. Okay. Then so let's okay, so let's write down in the definition of variation Hodge structure, part of the definition is that the flat connection decomposes in that way, okay, into 4 terms. And the 4 terms have the following properties. So the terms del and del bar, these have type 0, 0 in the fiber. You see, we're looking at, we have in the variation Hodge structure, we have a family of spaces that are indexed by DPQ. By PQ. Those PQ, those are Hodge types. They're the same indexation as goes with the complex value differential forms on the base. Okay.
So differential forms have an indexation PQ by Hodge type P and Q. P is the number of DZs and Q is the number of DZ bar.
Now the del, so in the fiber Hodge type, the del and del bar, those are operators that just preserve the bundles. They're operators that go in the same direction as each one of the subbundles. If we only had those operators, then our whole thing would just be a direct sum. Okay. And the del is the 1-0 type in the fiber, in the base. The del bar is the 0-1 type. Okay.
But now we have a phi and a p bar. So a phi is something which has type
1-0 in the base. And the p bar is something that has type 0-1 in the base. However, the type in the fiber is opposite. So the type in the fiber is -1, 1 here. And here it's 1, -1. So the total type, so the total type here is 1-0, 0-1. This total type is 0-1. The total type here is 1-0. Okay. So now what Deligne said to Steve Zucker was, let's organize this in the following way. Let's put these two things together in an operator that we'll call D double prime. Let's put these two things together in an operator that we'll call D prime. Okay. So we have, so nabla equals D prime plus D double prime.
Then what do?
We just, this is actually, even in terms of mathematics and linguistics, which is my new topic.
Even in terms of mathematics and linguistics, this is an interesting little gadget here, right? Because the prescription is just pretend that those are del and del bar. So just do everything you do, usual Hodge theory. But we pretend that the D prime is del and that the D double prime is del bar. Okay.
So now pretend that okay, and then the observation is that harmonic theory works. We have the Kähler, namely, we have the Kähler identities. Okay.
So this is, I think this is really the observation in Deligne's letter. There's a little subtle time change, but I'm not talking about having to do with the polarization. That time change is going to counteract the time change that we get by mixing up these two pieces. Making it so that the Kähler identities, you have the same, the usual Kähler identities work for the D prime and the D double.
Then you could just like erase everything, just erase all your dels and del bars and replace them by D prime and D double prime, and you don't really need to do any work anymore. And so this gives you a Hodge decomposition of HI of S with coefficients in V according to total type. Okay.
And so that works, that's just sort of formal, really.
And now using the degeneration theory, this still works when S is an open curve, so that's Zucker's.
I should say, so maybe historical comment is that the whole,
There was just a whole bunch of work by Cattani, Kaplan, and Schmid. Kashiwara, Kawai. Doing this in various levels of generality. Oh, yeah. Natalia had said something about approaching user limit here. And really, as it turns out, sort of a more, maybe more flexible and in the long run, maybe more powerful approach was Morihito Saito's. Also does that, Morihito Saito's theory also does that. And so an important point to notice is that Saito's theory, it uses Zucker's theorem. So Saito's theory is a way of sort of really formalizing, getting back to Lefschetz, formalizing Lefschetz devissage for this problem of calculating the cohomology of the local system underlying the variation of Hodge structure. So the idea is basically, if you have an n-dimensional, let's say a k-dimensional base, you want to calculate the cohomology on an open subset of a variation of Hodge structure, you should use Lefschetz vibrations on the base and apply Zucker's theorem at each stage, basically. Of course, it's highly non-obvious that the answer you get is independent of the choices of those vibrations. That's what Saito's theory tells you. Okay, so so using that, we can conclude that the variation of Hodge structure on the direct image local system over P1 determines the Hodge structure on the cohomology. Now, what about getting back to Alexander's question? So let me just remark here. So sort of a small remark is that the local system itself actually determines the Hodge coefficient. So okay, so maybe let me just go back up here. In modern non-ongoing Hodge theory terminology, this pair consisting of B plus the D double prime operator. So this is the del bar operator and the phi operator. That's what we call now a Higgs bundle. So in some way, these Higgs bundles showed up really already in Zucker's paper and Deligne's letter to Zucker, except they didn't actually give them a name, basically. But those are there. In fact, in Zucker's paper, there's a theorem about the Deligne cohomology of the base. What enters into that Deligne cohomology is exactly the Higgs field. So let me just comment that a small remark, which is that the local system actually determines its own Hodge coefficient. Why is that? So let's suppose, for example, n-1 is odd. Okay, the even case is actually easier by using orbitals. In the even case, the local system has a reflection of order 2 as monodromy at each of the points. So you can think of that as actually a smooth local system on the orbitals where you add order 2 orbital points at singular points. Or if you want to avoid orbitals, you can just pull back to a cover which has order 2 ramification of divisible by 2 at all over all the points. Okay. So let's suppose n minus 1 is odd. Then we have the Deligne canonical extension. B bar on P1. Okay. And this has this is the holomorphic bundle with a flat connection, flat logarithmic connection. So nabla goes from B bar into B bar tensor omega 1 P1 of log divisor D is the divisor. And the Hodge filtration is compatible with the canonical extension. This is part of the theory of degenerating variation of Hodge structure. So the Hodge filtration extends to a filtration F bar of, sorry, maybe I shouldn't call this bar. Let's go, keep the same F. Okay. We have a filtration on this bundle over P1. And so the little proposition is that GER, if we let E be GER F of B, then and so the point is that E is a direct sum of E P. And the connection takes E, sorry, the connection takes F P into F P minus 1 tensor omega 1 of log. Okay, so this is Griffiths transversality. That's part of the statement. I mean, that it's equivalent to, I mean, it comes from what I said before about the 4 operators, because the connection just has these 4 operators. The 2 operators that change the filtration, they change the filtration just by 1 step in each direction to restore. That's Griffiths transversality. Okay, so the proposition is that right, so phi goes from E P Q into E P minus 1 Q plus 1 tensor omega 1 P1 of log. This is the you might say the residual of what's known as what was always known in Phillips courses as the Kawai tensor. The Kawai tensor map. But anytime you have a connection and a filtration that satisfies this transversality property, you got the variation of the filtration by the connection gives you this map from the your E to your P minus 1 is decreasing indexation. Okay, so and what the proposition is that E comma phi is a semi-stable Higgs bundle. And in fact, stable if the representation is irreducible. And then another proposition is that if this GER is stable as a Higgs bundle, in other words, as a bundle with an operator, then there is a unique such filtration. Up to translation.
If the limiting, if the GER thing is only semi-stable, not stable, then you could sort of translate differently on different pieces, so to speak. So the uniqueness is not quite as good.
These are sort of the first part of non-ongoing Hodge theory, really. And it can be constructed also.
So in that sense, the local system determines the bundle with connection, the bundle with connection determines in this way filtration. So